Hey everyone, and welcome. Today we're going to crack a secret code, one that connects some pretty simple mathematical formulas to the beautiful shapes we see all around us. We are talking about polynomials. So let me ask you something to get us started. What on earth could a simple straight line possibly have in common with, say, the curve of a satellite dish? I mean, they look completely different, right? But stick with me, because by the end of this, you'll see they're actually part of the exact same family.
All right, so let's just dive right in. First things first, we gotta get the language down. What is a polynomial anyway?
Okay, so at its core, a polynomial is really just a mix of numbers and variables, like x or y. But here's the key rule. The powers on those variables, they have to be nice, clean, whole numbers. No fractions, no negatives, none of that messy stuff. And the biggest power you find in the whole expression, we call that its degree. You can totally think of it as its power level.
And this slide makes that rule super clear. Look over on the left. You've got your classic polynomials, like 4x plus 2 and 2y squared minus 3y plus 4. But then on the right, you see the rule breakers. Notice that? You've got a variable hanging out in the denominator or stuck under a square root. Yeah, polynomials just don't do that. That's a big no-no.
Okay, let's start with the basics. The simplest case, a polynomial with a degree of 1. We call this a linear polynomial. And yeah, you can totally think of this as our power level 1 equation.
So, what happens when you graph one of these? Well, you always, and I mean always, get a straight line. Every single time. Just look at this graph of y equals 2x plus 3. It's just a perfect straight line cutting right across the screen. Now, pay close attention to that one spot where the line crosses the horizontal x-axis. See it? That point is super important. It actually has a special name. We call it a 0. And for a straight line, it's really simple, right? One line, one crossing point, which means it has exactly 1 0. All right, so what happens when we level up? Let's move on to our next shape, the parabolic curve. This is our power level 2. And trust me, this is where things get way more interesting. So, a polynomial with a degree of 2 is called a quadratic polynomial. And its graph? It's that classic, beautiful U-shaped curve we call a parabola. This is literally the shape you see in things like satellite dishes, suspension bridges, or even the path a basketball makes when you shoot a hoop. Now, here's the thing. Unlike a straight line, a parabola has a few different ways it can play with that x-axis. So in our first case here, it can sweep down and cross the axis at 2 totally separate points. 2 crossings means, you guessed it, 2 zeros. Okay, case number 2. The parabola can come down and just kiss the x-axis, right at its lowest point, what we call the vertex. It only touches in that one single spot, which means it has just 1 0. And then there's our third and final possibility. The parabola might just float entirely above or below the x-axis. It never even touches it. So in a situation like this, it has no zeros at all. So just to recap what we just saw with our own eyes, a power level 2 polynomial can have at most 2 zeros, but it could also have just 1, or like we saw, none at all. 2, 1, or 0. Those are the options. Okay, now for the big reveal. This is the main event. We've been talking about the algebra, and we've been looking at the shapes. Now it's time to connect the dots and uncover the central secret of polynomials. So let's look at the algebra for this specific quadratic polynomial. If we take our formula, right, and we plug in the number -1 for x, we run the calculation and boom, the whole thing equals 0. Now, what happens if we try plugging in 4? Same deal. The result is 0. So keep those two numbers in your head, -1 and 4. And here it is. This is the connection. Look at the graph of that exact same polynomial. Where does it cross the x-axis? You see it? It's right at -1 and 4, the very same numbers. So the numbers that make the algebra go to 0 are the exact spots where the shape hits the axis. That's it. That's the secret code. So here's the bottom line. The word 0 isn't just some abstract math term. It is the literal physical point where the graph of the formula intersects the x-axis. That is the beautiful, powerful link between the equation and the shape it draws. Okay, so we've conquered power level 1 and power level 2. You know what's next, right? Let's take it to the next level and see if this pattern holds up when we jump to power level 3. What you're looking at here is the graph of a cubic polynomial. That's a degree 3.
it's a bit more complex, right? It's this wavy line. So, following the pattern we've discovered, how many times can it cross the x-axis? Well, as you can see, it can cross up to 3 times, which means it can have up to 3 zeros.
And this right here reveals a super simple but really powerful rule that works for any polynomial. The degree, that power level we've been talking about, it tells you the absolute maximum number of zeros it can have. A degree n polynomial can cross that x-axis at most n times. It's just that elegant. It's that simple. And if you can believe it, the code goes even deeper. There's another layer to the secret. You remember the standard form for a quadratic? Ax squared plus bx plus c? Well, those numbers out front, the a, b, and c, they hold their own secrets. Check this out. Without even finding zeros, you can know stuff about them. For instance, if you add the zeros together, their sum will always be equal to negative b over a. And if you multiply them, their product will always be c over a. It's this amazing shortcut that shows you just how deep the connection is between the numbers in the formula and the shape it makes. So there you have it. We've cracked the code. The degree tells you the shape's complexity, and those zeros, they're just where that shape meets the ground, where it hits the x-axis. So now that you know this secret language connecting formulas to shapes, I have a challenge for you. How many polynomials can you spot in the world around you? Seriously, from the arc of a water fountain to the curve of a bridge, once you see it, you'll start seeing them everywhere.